Everyone, uh, welcome to your physics class. Today is 17th of September 2020, Thursday, and in the physics we had almost covered half or more than half of the section in this chapter. In the last class we had completed the EMF of a cell and we had found relation between EMF, the terminal voltage and the voltage drop. Now let us go to the resistance. If you recall what the resistance is, in the resistance it is obstructions to the flow of current in a conductor. Now these resistances which was given by the symbol R. See, the resistance or the resistance which is given by the symbol R, and in the circuit diagram it is represented by this symbol. Okay. Now these resistance, or it is also called the resistor boxes, and if you take two or more than these resistors in a circuit or in a wire, then they can be combined in two ways. So today we will be doing the topic that is the combination of the resistors or the resistances. So please write down the topic. The topic for today is combination of resistors, or we can also call it as the resistances. Two or more than two resistances or resistors in a circuit can be combined in the following two ways. The first one is the series combination, and the second one is the parallel combination. Okay, so now first of all we will take up the first combination, that is series combination. This will be explained with the help of the diagram. You can also see in the textbook at page number 191. In the series combination, suppose we take three resistors. Let us name the resistors as R1, R2 and R3. In the series combination, let these three resistors are connected in series. Then one end of one resistor is connected to the other end of the other resistor, and the other end of that first resistor is connected to the terminals of a battery or a source of current. So what is happening here is basically resistors are joined one after the other. Okay, that is to say, in a simple terms, the resistors are joined one after the other. It is something like the bogie of a train. You see the trains, they have got each coaches, so one coaches after the another. So here we can do like this. Let R1, R2 and R3 be three resistances combined in series. Okay, it is combined in series. So now what happens is, in a circuit we will take the first resistance. Suppose this is R1, this is one end of the resistor and this is the other end of the resistor. So it has got two ends. Then this other end of the resistor is connected to another resistance, let us say R2. Then this is connected to another resistance, that is R3. Let us take that these three resistors are joined in series between the two end points. Let us say we have an end point A here and we have an end point B here. Now it is quite obvious and it is quite simple that the resistances are joined one after the other. See, one end of one resistor is connected to the other end of the second resistor. Similarly, this end of the resistor is connected to the other end of the resistor. Now, the two ends of the terminals, they are connected to a source of current, and basically the source of current is connected, it is a battery. So there is a key here and we have a circuit is completed now. So this is called the plug key, and this is the cell of the battery, the source of the current. Now what happens is, when this key is closed, when it is tapped, that means when it is connected, the circuit is closed or it is a complete circuit. That is circuit from the battery. Now what is the main purpose of the battery? To draw the current. So that current will start flowing from the positive terminal. It will come to the higher potential A because it is connected to the positive terminal, and we see that there is one path. There is a single path, okay, for the current to flow. So the same current will flow through all the resistors, and it will come out in the negative terminal B and again come to the negative terminal of the battery. So this is how we can combine the resistances. We have taken 3 resistances. There can be more than 3, or you can have only 2 resistances here. So in the series combination, what are the key points or the notes that you have to keep in mind? See, there are 2 key points that you have to keep in mind in the series combination. The first, what is the first thing? The first thing we observe is that the same current flows through the single path. The current remains same throughout the individual resistances. So same current, okay. The current, we have used the symbol I. Now if you see that from this positive terminal, the current I is coming. So when the current reaches the terminal A, now since this end is at the higher potential and NB is at the lower potential, because it is connected to the positive terminal of the battery. So at the positive terminal it is always at the higher potential, and at the negative terminal it is always at the lower potential. So the current I is coming here. See, there is a single path here. The same current will flow here. Here also same current, and the same current will come out of the last resistor R3. So the first thing you have to keep in mind is that the same current flows through the resistor because it has a single path. Now the second point is that if you take the total potential difference of the entire circuit, that means what will be the potential difference between the circuit of this will be V. Suppose this is the total potential difference of the entire circuit, and we observe that this potential difference of the entire circuit will be equal to the sum of the potential difference across each resistor. Now if you see that individually, look at the resistance R1, it has got 2 ends, so it has got its own potential difference. Let us say we take V1 as the potential difference of the first resistor R1. Similarly, R2 also has got 2 ends, so it also has its own potential difference V2, and similarly R3 has also got its own potential difference V3. So here what does it say? Let us say V is the potential difference of the entire circuit, and this potential difference is equal to the sum of the potential difference of individual resistors. So in the series combination, the key points that you have to keep in mind is the resistors are connected or joined one after the other, like the bogie of a train in a straight line. Then second point, the same current flows through each resistors, and third point, the potential difference of the entire circuit, that means V is the potential difference of this cell or the entire circuit, that potential difference will be equal to the sum of the potential difference of individual resistances. Okay, so now from this we are going to find the equivalent resistance. So that is the most important topic here. Equivalent resistance of in the series combination. Equivalent resistance. Equivalent resistance can be also taken as the total resistance, or it can be also taken as the total resistance, or the that effective resistance. Effective means, now see how many resistances are there? 3. So they can be combined and made it into one. So that one will be the equivalent resistance of the entire circuit. So for that we have to use Ohm's law. So I am going to derive how you are going to get this. If you look at this first resistor, just now consider the first resistor R1. What is its potential difference? V1. What is the current flowing there? I. So what is the Ohm's law? V1 equals to I R1. This is for the first resistor. Because the potential difference is V1, the current flowing is I, and the resistor is R1. Similarly, when you come to this region, in this resistor, what is the potential difference? V2. And what is the resistance? R2. But here also the same current I is flowing, so we get like this. V2 equals to I R2. This is for the second resistor. Since we have taken 3 resistors, so we also have for the third one, that is I R3, because here the current remains same throughout the resistors. Now you have just learned that V equals to V1 plus V2 plus V3. Okay. So now this V is for the entire circuit. So what will be the resistance? So that resistance for the entire circuit is called the equivalent resistance. So we can take the current is I, and you can take IR, or you can also write as RS, because it is this resistance is the equivalent resistance for this complete circuit. Now V1 is given here as I R1, V2 is given as I R2, plus V3 is given as I R3. So what do you see here? We see the two sides. That equation is formed here, and on both the sides the R is common. So when that I is removed, we get like this. So this is the equivalent resistance. Equivalent resistance of the entire circuit when the individual resistors R1, R2, R3 are combined in series. So what do we get from here? The equivalent resistance of the entire circuit is equal to the sum of the individual or each resistors. So I will repeat this again. The equivalent resistance of the series combination is equal to the sum of the individual resistances. Now if there are more than 3 resistors, for example if there are n resistors, then we get something like this. You go on adding up to n. So there can be more than 3, 4, 5, 6, or that means 2 should be the minimum. If there are 2, then you just add R1 plus R2. So this formula is very, very important here. So from this, you can refer to your textbook in page number 191 and 192. You will find the note at the end there. That means these two you have to write down. If you look at the total resistance the total resistance in the series is always greater than the individual resistance. The total resistance, or we can write down equivalent resistance, is always greater than each resistor in the series circuit. Okay, like for example, if the value of this resistance is, let us say, 2 ohm, we know that ohm is the unit of the resistance. Let us say value of the R2 is 3 ohm, alright, and let us say the value of R3 is 4 ohm. This is just given randomly. Now these three resistors with 2 ohm, 3 ohm and 4 ohm, when they are connected in the series, what will be the equivalent resistance? That means the single resistance of this, it will be 2 plus 3 plus 5, that means 9 ohm. So 9 ohm will be the equivalent resistance. So this type of numericals will be there in the series combinations. Okay. Now we will be going to the next combination, that is the parallel combinations. So I think the diagram is clear there. It's very, very simple. Just try to recall the train, the bogie of the train connected, or it is connected or joined one after the other, and same current is flowing. Now let us do quickly the second type of combination, that is the parallel combination. So let us take here also three resistances, R1, R2 and R3, be connected in parallel between the two points A and B. Alright, so let us write down number 2, parallel combination. So we have in this case also taking three resistors. Let R1, R2 and R3 be connected in parallel between the two endpoint A and B. These are the two endpoints. So what happens is, in the parallel combination, one end of each resistor is connected to the same point. It is something like this. See, let us take, this is resistor R1. This is one end and this is the other end. So here what it is saying is, one end of each resistor is joined at the same point. Let us take resistance R2 and let us take resistance R3. So we have got three resistances. It is kept in a pile up. Okay. Now these are the same end, one end. The one end is connected to one point and the other end is connected to the other point. So let us take, it is connected to, let us say, point A. Okay, like this. Then we have the other end. Let us say this is connected to the point B. So this is how the parallel combination looks. In the series, it was joined one after the other. In the parallel, it is joined one above the other, or one below the other. Okay, one after the other in series, one above or one below the other in the parallel, and the same one end is connected to the same point and the other end is connected to the other point. Now these two ends of the terminals are connected to a battery through the help of a plug key. It is like this. Okay, so this is the battery, the source of the current, or we can also call it as cell. Battery is actually the combination of cells. Anyway, that will not go into that. This is the plug key, and when the circuit is closed, the current will flow and it will come to the end A. When the current reaches the point A, now see very, very carefully what happens. When the current which is coming from the battery after the circuit is closed, it reaches the point A, then it will divide it into different segments. So see, the current will split up. It will go I1 because I have taken the R1. The same will go there I2, and it will go there I3. Then this individual current. So this current has decreased here. A small portion of the current is going through R1, some portion is going through R2, and some portion is going through I3, and they will all come here, and it will rejoin at the point B. Then from the point B, the total current will flow back to the cell. So this is the diagram for the parallel combination. Points to keep in mind is the current I divides itself into different paths. The current I divides itself into different paths along each resistor. Okay. Then what do you observe here is this current that is passing through each resistor will be inversely proportional to the resistance. It will be inversely proportional to the resistance. So if the resistance is more here, the current will be less. Okay, obviously that is the relation between the resistance and the current. So current is inversely proportional to the resistance. If the resistance is more, the current will be less. If the less resistance, then more current will flow. That means accordingly it will balance that. Suppose if these three resistances are of same value, then same current will flow. But if this resistance is less and if this resistance is more, then here more current will flow, then less current will flow here. Okay. And second point, what do you observe here is the total potential difference for the entire cell. Suppose if I take it as V. The total potential difference between the point A and B, that means for the entire circuit, this potential difference will remain same for the individual resistor. So for the resistor R1 also you will have the same potential difference V. For the resistance R2 also you will have the same potential difference V, and for the resistance R3 also you will have the same potential difference V. So potential difference V remains same for each resistor. I'm just writing R. Please, you have to get the get it that this is a each resistor means individual resistance. So a quick recap of the series and the parallel. In the series they are joined one after another, okay, like this in a straight line, whereas in the parallel it is joined vertically. Vertically, series is joined in the horizontal. In the series, one end is joined to the other end. Here, one end is joined to the same point. And in series, the same current is passing through each resistor, but here the current is split up, or it is divided into different sections. In the series, you have the different potential difference for each resistor. In the parallel, the potential difference is same for the entire circuit, and that will be the same potential difference for individual resistors. Now let us find the equivalent resistance for this parallel combination. Let us find equivalent resistance for this parallel combination. So write down equivalent resistance. As I have already told you, equivalent resistance is same as the total resistance, or it is same as the effective resistance. That means we have to reduce this into a single resistance for the entire circuit when they are connected in parallel. So we can write this as RP. Suppose P stands for parallel. Let us use the Ohm's law here. V equals to, here the potential difference is I into R, I1, R1, or you can take I1 as V upon R1, make this equation 1. This is for the first resistor. And if you look at the second resistor, you have V equals to which current is flowing there? I2. And what is the resistance there? R2. So from here, I2 will be V divided by R2. Keep in mind the V is remaining same. And through the third resistor using the Ohm's law, the current flowing is I3 and the resistance is R3. So from here, I3 will be given as V upon R3. So this is third equation. Okay. So now if you look at this, the current here this current is splitting up into three currents, so it will be the sum I1 plus I2 plus I3. Okay. Now this I is the current for the entire circuit, and the potential difference for the entire circuit is V, and we have also taken the equivalent resistance. So what will be the formula here? V upon RP, like this. Okay. What was I1 you got just now here? V upon R1. I2 what you got? V upon R2. And I3 what you got? V upon R3. I have to rub this slightly. So let us take this quickly now. So after looking at both the sides, the V will be cancelled from both the end. So we will get that like this. So this will be the equivalent resistance in the parallel. So what do we see here? We see that it is a reciprocal. That means the reciprocal of the equivalent resistance in the parallel combination is equal to the sum of the reciprocal of individual or each resistance. So it is in the reciprocal. That means what do we observe is the total resistance we get in the parallel. The total resistance, whatever we get in the parallel, that total resistance will be less than the individual resistance. Let us take example. See, suppose R1 is 2 ohm, R2 is 3 ohm, and let us say R is 4 ohm. Okay. Suppose this is just a random value given there. R1 2, R2 3, R4, R3 4 ohm. So let us check this. What do you get here? 1 by 2 plus 1 by 3 plus 1 by 4. So let us add this quickly by taking the LCM. I think it should be 12. 6, 3 4s are 12, 4 3s are 12. So we get 10 plus 3, 13 by 12. So if you reciprocate, you will get 12 by 13. 12 by 13 is obviously a very small value. It will come in the decimal point. It is less than 1. So look at this. Look at the first resistor, 2 ohm. This is more than the equivalent resistance. Yes or no? So this equivalent resistance will be less than all the individual resistances in case of the parallel, whereas in case of the series, the equivalent resistance will be more than the what you call individual resistances. So these are the two formulas we have learned here. Now you will get a lot of numericals from there, a lot of diagrams will be there. So when we come back in the next class, we will be discussing some questions, okay, there from the textbook, and these questions are there in page number 200, that is exercise 8b. Before we start the numerical, you have to do exercise 8b, page number 200, question number 1 to 10. Please do it yourself in your exercise copy. Now there is one question in that, that is question number 11. if you see there, the VI graph for a series and the parallel of two resistances are shown in the diagram. Okay, so I'll just do that quickly. Question number 11, page number 200, exercise 2B. There is a I and V. Okay, and there are two straight lines are given, B and A. Now you have to which of the two line A and B that will represent the parallel combination, which will be the parallel. So first of all, you see that the slope in the VI graph gives you the resistance, yes or no? It gives you resistance. So obviously this line A is less steeper than the line B. That means it has got less resistance. So in which case you have a less resistance, in the series or in the parallel, the total resistance. So in the parallel you have got less resistance than the individual resistance. So therefore the line A represents the parallel combination and the line B represents the series combination. So like that, there are what you call numericals in the next section. That means in page number 201. So that numericals we'll be doing in the next class. So till then, you need to understand the concept. I think it is very clear. In the series, you just add them. In the parallel, you have to add in the reciprocal. Thank you very much. Have a nice day.